I hope at the end of the day, you feel this presentation is helpful and for your hands-on and case study in fine-tuning for semantic search. Okay, let's get started. So here is the general outline of this presentation today. So firstly, I'll introduce what we have done for Rakuten in semantic search. And then I'll introduce how to apply LLM as encoders, and also introduce a very interesting and famous series of embedding models of QN3 embedding. And last but not least, I will show you a case study of hands-ons of QN3 embedding model parameter efficient fine-tuning, PEFT. Okay, so firstly, allow me to give a brief introduction of myself. So I'm currently working as a principal research scientist at Rakuten, leading and managing a machine learning team, very small team, but our focus is big. So we include semantic and multimodal search technology, especially for Rakuten e-commerce marketplaces. And also, we want to apply the cutting edge technology for multi-channel retrieval, as well as multi-objective ranking. And at the same time, we target to apply and study the next generation search model powered by the novel LLM architectures. Okay, and also we are targeting to apply the personalization with the wave of this Gen AI and try to figure out what are the user intent throughout the search journey and also to uplift our shopping revenues. And here I give this photo. It's very beautiful photo. So this is taken in this July when I visit Mount Amulo in Izu, Japan. So it's a very beautiful cinder-cone volcano. So hopefully you can also visit this place. It's very nice. Okay, let's get started our main topic. So firstly, I will talk about what is semantic search. Okay, so here if you have this experience before. So for example, you don't have a quite word of what you are trying to search. For example, you can't remember the name of your favorite tea from England, and you just remember like the origin place is from England and it's black tea maybe. And then let's see. So if you try to search that using a search query, let's say you type in a sentence as explaining what it's like. And in the previous Ichiba, or as Zoe introduced, is our main e-commerce marketplace in Japan, domestic e-commerce business. And previously, you will find zero hit, which means there's no results return if you search using this keyword. And this is very bad case. Sorry. I don't know what happened, but let me try reconnecting. Right. All right. So after you got this zero hit problem, you're trying to refine your search query so that you can get better results in terms of search. So the first thing we usually do is the users will need to manually split their keywords. For example, here, this is in Japanese, but you can consider we try to manually split the Japanese because Japanese, naturally, there's no white space in this language, right? But users will need to split or tokenize their search queries so that they can separate England, famous, and tea into 3 tokens. And then they will see a whole bunch of tea products came out. But when we look at the results, do you think the results are good, given the user intent of British tea? Obviously not, because you can see all different origin places tea showing there. So basically, the previous lexical search only captured the meaning of tea, right? Without the real user intent of the original place is British tea, other than German tea or Indian tea or Taiwan tea. Yeah. All right. So now you see the tea called Williamson tea if you apply our new semantic search. So this is actually released 2 years ago on Ichiba. So now without splitting the keywords into tokens, right? You just put the original keyword search. And then we not only apply a lexical search, but also semantic search. Then the semantic search, where in the back end you have AI and the deep learning technologies, actually extract the meaning of the user intent using some form of embedding, if you're familiar with this, and realizing the semantic-driven search experience. So this actually uplifts the user experience in terms of semantic search as per user intent. All right, sorry, I think I go. Yeah, let's come back to this slide. So actually, this reveals the first and the most important benefit of employing semantic search is that it can significantly reduce the zero hit ratio for the end users in production. So this is the biggest benefit of semantic search, regardless of how relevant your algorithm can bring to the user. At least you reduce the zero hit rate. Okay, and in other words, the impression of the relevant items got boosted, and it bring in potential clicks and also potential purchases as per user's intent. So at the end of the day, we're talking about revenue and the GMV and click CVR uplift in production. And another benefit that semantic search bring is the robustness to cover misspellings and typos. So in this case, if we have a typo, and although this Nike was misspelled, as you can see previously, using lexical search only, you will get some Nike product, but they're not Air Jordan. But by applying semantic search along with lexical search, so although we have some misspellings, but still the results are quite related or relevant to the user intent of Air Jordan, and all the results are Air Jordan shoes. Okay. And also, as more and more foreign employees and victors uh, move to Japan or travel to Japan, the potential demands of multilingual assistant to purchase their necessities is huge. So to that end, we target to onboard those customers and enhance our semantic search model with multilingual support. So far we've covered English, Korean, Chinese, Vietnamese, alongside Japanese. Right. Okay. So you may wonder, how does semantic search work, right? So actually, what behind this semantic search is an algorithm called vector-based search, and also known as embedding-based retrieval. Okay. So this is what a vector used for semantic search look like. So in this diagram, as you can see, maybe to a human, they're just numbers, right? They are like a series of 300 dimensional vectors. But to AI, it's actually knowledge. It's a huge knowledge base that we store all the semantic meanings behind or underlying these embeddings. And by storing and make use of these data and objects to this vector embedding space, we're able to store all this knowledge in a knowledge base. Okay, and using some modules such as two tower or bi-encoder model, that we can apply our search queries and item information into this vector database, we're able to learn and obtain the query and item information by vectors. Okay, and then these vectors can be searched through an algorithm so-called AN, approximate nearest neighborhood, using the state-of-art vector database. And this is what we have for semantic search in production. All right, now let's open the magic box of semantic search in terms of machine learning modeling. So this is maybe the mainstream of this tech talk of machine learning related topics. So speaking of models, or maybe one step back, when we talk about the technology itself, right? When we say vector-based search or semantic search, another perspective from research is that we call that embedding-based information retrieval. So in many research papers, you will see this EBIR. So this is actually the idea of how we apply the embedding-based retrieval in production for semantic search. So in this diagram, I showed two architectures. So do you guys know what is the left-hand architecture called in EBIR? Anyone familiar with sentence transformers? Okay. So basically, the left-hand architecture is a bi-encoder model. So one characteristic is that in this bi-encoder model, we have query and results or document, parse, whatever you call it, in two separate encoders. Okay. Then we call this bi-encoder. Sorry, I think I got kicked off again. So sorry for the Wi-Fi issue. My Zoom got disconnected. Now it's back. Okay, where were we? Okay, yeah, I think it's the bi-encoder model. So basically, based on this diagram, as you can see, we have two encoders separately. One is so-called query encoder, the other one is result encoder. And then the applications of this bi-encoder includes image search or semantic search, as we can see. And in contrast, we have the right-hand diagram or architecture. And this architecture is so-called cross-encoder. So actually, this is very popular and famous of cross-encoder in terms of classification task. So one characteristic is that in this cross-encoder output, as you can see, it output a score instead of a results or embedding. So actually, this score is either 0 or 1. So it's very powerful in by class classification. Okay. And actually, in practice, when we talk about search or semantic search, this cross-encoder has been widely applied to the re-ranking stage. So usually we have LTR learning to rank, and after re-ranking, the most state-of-art architecture, we apply this cross-encoder as the last layer so that we can have very fine-grained ranking stage using this cross-encoder, but it's very costly. Yeah. So if you have a top 10 re-ranking using this cross encoder, it will cost maybe triple times of your all previous stage of retrieval, ranking, and re-ranking. So that's why it's not very common to be widely used in production. Okay. And as you can see in semantic search, when we talk about models, then we are talking about byte encoder. And in production, we also call this two-tower model. So you can imagine we have two towers of encoders, right? One is so-called query tower. The other one is product item tower in our e-commerce use case in particular. All right. Okay. And more recently, we have another series of transformer-based model. And this is maybe not directly related to retrieval, but the model architecture-wise, as you can see, there are also transformer models, right? But they are decoder only, so there's no encoder. Decoder, when we say it, is basically the transformer model that we use causal attention instead of bidirectional attention. Okay, and given a query, instead of generating scores or embeddings, we are generating natural languages, for example. So it's quite sequence to sequence model. And some example including GPT, right? And also this architecture is from GPT-2. And ChatGPT or translation task, when we try to generate stuff, then yeah, this is the model that we're talking about nowadays. And also this is the foundation of the most of the LLMs nowadays. They're using decoder only model. All right. So as I said, so LLMs or GPT models, they are decoder only models. So, but in contrast, we have encoder only model for our dense retrieval or embedding based retrieval, right? So how can we bridge this decoder only model and make them usable in this encoder context? Okay. So some explorations back in 2024. So it's actually last year, but things move very fast in the recent 5 years as the event of this LM stuff. So one paper is quite insightful. It's called LM 2 back. So this is kind of the first fundamental or really applicable method that we can really make use of decoder models in this encoder use case. Okay, so actually they have very simple ideas behind. So basically 3 steps of how that we can transition from decoder only model to encoder model. So firstly, they enable the bidirectional attention to outcome the limitation or restriction of this causal attention so that they convert the behavior or characteristic of decoder left to right behavior or manner to this bidirectional attention behavior. And then secondly, they adapt this model to use bidirectional attention in this mask next token prediction task. So this is similar task as BERT did, right? If you remember BERT, when BERT do encoding, and then their training objective includes this mask next token prediction, okay? So in particular, this LM to VEC, they apply this bidirectional attention model to this task. And thirdly, they apply an unsupervised contrastive learning. So this is also a very important step that they can match the embeddings between the one dimension to the other. Okay, so in this case, if we have dense retrieval, then you have query to items. Okay, and here there's a very interesting thing is that during their experimentation, they find that mean pooling learning were performed the best to learn a better quality of embeddings in their SIM CSE task. Okay, let's take a closer look. So if we talk about like embedding, right? So in this LM model or decoder model, even we apply this modification in the model architecture and also the pre-training task, how to extract the embedding is also very tricky. Using different method will give you different performance in the end, okay? So in this paper, they mentioned 3 methods of how that we can extract embedding from the trained LM models, okay? And this is related to pooling. So the first method is called mean pooling. So where we average all the token hidden states. So here is very important because we have many tokens and all of them has the hidden states. So how to balance the hidden state and retrieve the best embedding is very tricky. Okay, so the first method is just a very simple one that we just average all token hidden embeddings. And the second method is a little bit complex that based upon the first mean pooling, for example, we can learn some trainable weights that we dynamically assign the importance to these tokens, okay? And then in weighted mean pooling, then we basically apply this learnable weight to the mean to the average of all the token hidden states. And of course, we can also have weighted sum pooling, where we can add this learnable weights to assign the importance to the sum of these token hidden states, okay? And the last one is very interesting. It's called last token pooling, where we append an extra token, EOS, to the end of the sequence. And then we use its hidden state directly. So we don't do mean pooling or weighted pooling. We just use the last token hidden state as our embedding in the end. So as I mentioned, as a result, this LM2VEC paper conclude that although they can be compatible with all 3 methods, but it works best with the bidirectional attention plus mean pooling, the first pooling method. All right. And besides fine tuning, actually prompting has been increasingly popular nowadays. And when using efficient fine tuning via contrastive learning, we're able to gain knowledge enhancement from instruction for text embedding. So here I want to introduce a framework. It's open source, so-called QN3 embedding series. So this is actually the new MTEB, Massive Text Embedding Benchmark, SOTA results, okay? So this is very significant advancement over all its predecessors. So for example, in Qwen, they have GTE, General Text Embedding, Qwen. But this Q13 actually outperformed that because it actually built upon the Q13 foundation model in this text embedding and re-ranking capability in particular. So here's some key features of Q13 series. So they have two series, as I mentioned. One is embedding models. The other is re-ranking model. Given the time constraint today, I would only talk about the embedding series. So here, as you can see in the embedding models, we have LLMs with causal attention. So there's no bidirectional attention anymore. And also they make use of the last EOS token pooling. Okay, so they append this EOS token in the end. And then their final embedding is actually getting the EOS token hidden states. Okay, and but in addition to the previous two steps, actually the instruction tuning is the most important step here. So actually they change or modify the query input format and also the document input format so that they can apply this instruction tuning in their pre-training task and make all this embedding more task aware, right? Okay. So this series inherits with the incredible multilingual capability because the Q13 foundation model actually support multilingual. And in some particular task, for example, the long context understanding and reasoning skill set is actually also inherit the capability of the Q13 foundational model. And the Q13 embedding series also represent a significant advancement in this embedding and re-ranking task, as I mentioned, the MTEB benchmark. Okay. So here, as you can see, they provide a whole series of models from the smaller one, like 0.6B model, up to 8B model. So if you're interested, you can actually experiment with a different size of the model and explore why like 0.6B is actually the most popular one because it's quite lightweight and it's not even a SLM, small language model. It's actually a very compatible model with most of the architectures and it's closer to the on-device models as well. Because if you reduce your model size down to like less than 1B model, then it's kind of possible that your iPhone or Android phone using the most cutting edge chipset can support this model directly on device, okay? All right. So our last part, I will introduce a hands-on case study that actually given this Q&A embedding model, right? Given our dense retrieval task, how can we fine-tune this Q13 embedding model so that we can make use of this advantage of this LLM embedding in our dense retrieval task in particular, okay? And here I show a use case that we can actually reuse the Microsoft Marco dataset. It's a very famous retrieval data set, but let's see how can we apply this in this Q13 embedding fine-tuning. So yeah, here I actually list down very detailed step-by-step instruction, like how you can also try this. Maybe after this tech talk, if you're interested, you can try to set up your virtual environment and also install a very interesting fine-tuning framework. It's also developed and published by Alibaba. It's called MS Sweep. So this is the scalable, lightweight infrastructure for fine-tuning. So by the name implies, if you are interested in fine-tuning the LLMs, including the SFT, like the full SFT, or PEFT, like LoRa, or even later you want to apply RL algorithm, like GRPO and etc., that you can all make use of this package for whatever fine-tuning task you are interested. Okay, and also for this tech talk, I will experiment this very quickly using this sweep package. And then we just install some other dependencies of transformer models and also flash attention to accelerate training. And the step 4 is we download this MS Marco dataset using this Hugging Face hub. So you know, like if you are installing this Hugging Face hub, you are able to download the models and also dataset easily. All right. And then it comes to a very important step that given the original MS Marco dataset on Hugging Face, for example, so the original data framework is not directly usable in our Q13 or whatever LLM fine-tuning jobs, right? So this is a very typical LM SFT data format. So always start with messages and also some like positive messages, and you need to specify the roles and the content and etc. So the first step when I downloaded this data set, so I did this conversion, right? So I need to convert the data format from the original Hugging Face data format to this Swift compatible data format above. All right. And then it's come to the most important step of this fine-tuning case study is that we want to implement this fine-tuning by integrating the low-rank adapters into the fixed backbone or frozen backbone and train them using the contrastive loss. So here, in particular, we have this info and CE loss. Later, I will explain this. So a couple of rationales. So first is that given these large language models, they typically contains hundreds of millions or even tens of billions parameters. So doing a full fine-tuning requires a significant amount of computational resources and storage. And the second problem is if we do a full fine-tuning process, so maybe it will directly remove all the memory, the good memories of language understanding and reasoning capability of the original pre-trained model, so that we don't want to erase all these good memories, okay? And maybe the other reason is that many fine-tuning methods can actually increase this computational latency during inferencing stage. So actually, if we want to consider the real-time application in production, then doing some parameter efficient fine-tuning is more practical. Okay. Yeah, so this is the general introduction of this inference CE loss. So I put it in this slide because I feel this loss is very interesting. It's contrastive, so-called contrastive loss, but if you look at it, it's very similar to cross-entropy loss, right? So if you're familiar with cross-entropy, so as you can see, only two modifications has been done here. The first one is in the exponential, you have a similarity score instead of the logits, right? And then which means if we include the similarity, cosine similarity, for example, between the sample pairs, and then basically you have this contrastive learning. And also the other additional component is this temperature parameter. Okay, so if this temperature is equal to 1, basically you have a cross entropy loss, right? So we don't add any temperature parameter to tune the importance of these sample pairs. Okay. And this is kind of the LoRa 101. If you are not familiar with what is low rank adaptation, then hopefully you know or heard of matrix factorization. So this is related to this LoRa, right? When we talk about like low rank matrix factorization, then this is the LoRa basically. So on the left hand side, we have the full SFT. So here the trainable weights is actually this delta W. Okay, so given the pre-trained W is having the dimension of D by D, then your delta W has D by D as well. So basically your final fine-tuned model will concatenate them or add them, sum them, the pre-trained weights plus delta weights. Okay, and in terms of computational complexity, basically you have quadratic or n square, or in this case, D square complexity. And on the other hand, if we consider LoRa, then it's very interesting that your delta W now is actually B times A. And in this case, you have A is a normal distributed matrix and B is a zero matrix. And the first step is that we set objective. So we have a very high dimensional matrix, delta W. As I mentioned, is D by D. Okay, so we aim to approximate it with two low dimensional matrix A and B, which is yeah, like delta W is equal to B times or multiplied by A in this case. And then we set the dimension of A and B matrix. So in this case, R should be much, much less than the dimension of D. Okay, so A has the dimension of R by D and B has the dimension of D by R. So at the end of the day, you will have this delta W with the trainable parameters of D by R plus D by R. actually, or R by D. Okay, so instead of you have D by D, now you actually have the sum of two lower rank matrix. So that's the idea behind this matrix factorization and how we save these training costs of parameters, right? So I always want to show you some very simple algorithms or coding to explain or demonstrate this algorithm. So in this case, let's use NumPy only, okay? So we just simply initialize this matrix W. As I mentioned, the pre-trained matrix, you can assume is D by D, and in this case, it's 4 by 4. Okay, and then we set a rank of 2. You can consider it's half of the original dimension 4. And then we just randomly initialize A and B matrix like this. So what's next? So in the next case, you actually have the optimization and training. So also in NumPy, so everything is in NumPy. There's no PyTorch or Hugging Face. You just do this loss or back propagation in this loss study. And our task is to approximate this delta W given this low rank matrix factorization with respect to this original matrix W. And here I show from epoch 0 to epoch 1000 or 900. As you can see, the loss keep decreasing, right? And if our target is to approximate this matrix factorization from the high dimensional matrix W to two lower dimensional matrix A and B. So this is the results. As you can see, we have done very good job. Your W approximate has a very good fitting to the original W after 1000 iteration of training. Okay, so it's clear. Right, so let's come to back to our Swift fine tuning. Okay, so I would just want to show you the simplest code that we can trigger this fine tuning using Swift on this QN3 embedding model. So in this case, actually I load this 0.6b model, and also there's very important step that we specify your training type. So in this case, we have this training type of full, which means we do a full SFT, and the task type is actually embedding, so which means Swift already support this fine tuning of embedding model using QN3. Okay, so we actually validate we are doing the correct thing because actually, if you look at the model parameters, then all the parameters has been tuned and trainable. Okay, it's 100% trainable case. On the other hand, if we trigger this LoRa tuning using this QN3 and also um, on Swift, so as I highlight here, actually you can specify to LoRa, and then instead of doing full SFT, so let's see what we have. So if you set your rank R value to be 32 in this case, so only around 3.5 or more or less parameters will be trainable. So all the parameters in the backend model will be frozen. Okay. So as this two pie chart shows, as you can see, like it's very efficient if we only do LoRa tuning, right? Regardless of performance at the moment, right? So after you do this LoRa tuning, and the next step is a must-have that we need to merge this LoRa tune parameters back to your original backbone model, right? And it also in Swift they support this. You just call Swift export, then it will merge the LoRa ways in this path back to your base model path. Okay. And let's see what we have after immersion model. So I also show you how that we can try the encoding of the query and document. So here is also another evaluation data in MS Marco. So let's see the scores. So as reference, you can see QN3 embedding is our base model, give you this certain similarity score, 75 and 84. And if we do SFT, which is a full fine tuning, then your like similarity score will increase to 83. But surprisingly, by only tune or train or LoRa tuning, like 3% of the whole parameters, we got even higher similarity score, 85 for the first pair and 82 for the second pair. Okay, so it's quite powerful considering the tunable or trainable parameters that we have done. Okay, let's take a closer look and conclude this presentation. So as you can see, the training efficiency got a very good gain. So around 97% of parameters has been reduced in your fine tuning, right? We only train like 20 million parameters and froze all the other 97%. And also the similarity score got boosted compared to your base model without this lower tuning in your MS Marco task. Okay. And therefore, the key takeaway from this talk is that although LoRa is very simple idea, but when you try to specifically fine tune a task on your data set or your task, you given a large language model, right? So here I show the case of 0.6 billion model, but of course you can fine tune a 8B QN3 model or 4B QNB model, right? So depends on your requirement and your computational resources. But always start with lower tuning will give you some benefits, right? Before you do a full fine tuning. So this PEFT is always a good choice to try first. If you achieve the certain performance that you require, then that's very good story to tell as well. Okay. Right. So that conclude today's presentation. Sorry, I'm a little bit over time. Yeah, but I'm also welcome any questions. Do you have any questions? Yeah. You mean the LM fine tuning? Yeah. Yeah, I think that's definitely one of the options. So in the current production, we're not using LM models for sure. Is too costly, and also we have a very strict QPS and latency requirements that we cannot fulfill using the LM models. And definitely, like even 0.6 billion might be too large, to be honest. And also another bottleneck is the dimension of vectors. So here I present the vectors, right? But actually the vector dimension make a very big difference. So consider if you want to deploy a 4096 dimensional vectors from a large language model, then actually the vector dimension itself cannot host in the production easily. And obviously it's very common that in the industry, we distill or we actually downgrade our vector dimension down to 100 dimension or 128 or even smaller so that we can store the data. Otherwise, also storage is another bottleneck. Yeah. So before we figure out a good way that we can make it compatible with our production pipeline and engineering infra. Yeah, it's still like some moonshot. Yeah. Thank you for your question.
Hi, I have one question. So, when you do the dimensional reduction, right, and also when you compare between the zero point 0.6b to the higher bigger models, what kind of questions can the bigger dimension or bigger models do that the smaller models cannot do?
You mean in this semantic search
Yeah, yeah.
scenario? Yeah, I think it's actually limited to the sequence length. So for example, before we apply this large language model using a BERT, it's very common that you have a few hundreds of sequence length as your maximum limit, right? So which means in the semantic search scenario, even given a very long product item description or titles, you cannot easily consume all of them because you always have the threshold you need to cut off at like 500 or 512 tokens, and then regardless what how informative or meaningful of the rest, you need to disregard them, right? You only focus on the previous 512 tokens. So that's maybe one a big reason I believe applying this large language model will be beneficial because we can look longer context in terms of semantic search and information retrieval.
So is the main problem just the sequence length, or is there like, let's say, same sequence length, but then different complexity of questions
Yeah, it
or
actually
answer pair?
depends on. So in this very practical use case in search, so in e-commerce, I have to say, Our e-commerce usually educate our user as well. So for a long time, if your user cannot get their results, then they keep fine tuning themselves, right? They refine their text queries, limit themselves to keywords, and this is actually less semantic, right? Like when we talk to ChatGPT, you always ask very long questions, but you rarely see this behavior in your search queries in e-commerce and maybe other domains. So it will take some time. The users will need to be adapted to this new experience of search as well, not limit themselves. Yeah.
Thank you.
Yeah. Thank you. Yeah. Yes, yes, that's a very good question. So in production or search product, if you can well define your task, then before you go to model training or data collection, evaluation, benchmark, and metrics is the most critical thing you need to figure out first. Otherwise, although we can debug these models using offline metrics, you can use NDCG or recall precision, whatever metrics, you still have the gap towards the online metrics. We need to do A/B tests at the end of the day, and then your CTR, CVR, and also the revenue will be the final metrics, right? So that's why, as I said, the evaluation metrics and benchmark is the most crucial part. That if you have a very good alignment and correlation, then you're very lucky. So whatever model you develop, it must be a success. Otherwise, you're just wasting your time in this circle. Yeah. Thank you.
Any other questions?
Thank you so much for the talk. You mentioned that in production, you have to compress your embeddings to a low dimension and even all the way to 100. Do you mind sharing a few insights? How do you achieve this compression?
Yeah, that's a very good question, very practical. So basically, when we train our model, for example, if you have a bird model and then you just try with the original embedding size. So this is what paper or technical reports give you the best performance. And then you don't limit yourself at this stage. You just try to pursue the best performing model in your particular evaluation benchmark and metrics. Try to see the maximum performance there, and then you also have some expectation of your final performance, right? And then you know like what is the room for you to downgrade or fine tune your vector space. So given a very big room, then you know like you can greatly reduce your dimension of vectors, right? Maybe by 5 times or 6 times, you can still remain the expectation, and then you can and then the benefit of a smaller size of embedding will actually save your cost of inferencing, right? And then from engineering perspective, they'll be very happy because you save costs, and saving costs is also another uplift of your revenue and ROIs, right? Yep. Thank you.
Is there one last question? And if not, let me thank our speaker.
Okay,
Thank
thank
you
you,
very much.
everyone. Thank you.
And- Okay, we've got a bit of Zoom technology to play with. Oh, that's great. That. Okay, poorly done. Okay, so I've just got a lightning talk. I'm going to talk about the IFO Gold using agentic Gemini. And yes, so I guess just a little bit about me. One question, how many people have been to our meetup before? Okay, how many people is this the first time they've ever been to a machine learning meetup, machine learning Singapore meetup? Okay, so one or two new folk from the city center, I guess. So I've got a kind of background in machine intelligence and finance. I moved to Singapore in 2013. 2014 was like a sabbatical year where I just did fun. 2015, I've been more like Singapore serious mode, essentially making papers for fun. Google has made me a Google developer expert. And along with Sam, I organized the ML, Machine Learning Singapore thing. It used to be called the TFNDL, the TensorFlow and Deep Learning Meetup, back in 2017. We also have a small company called Red Dragon AI. And with that, we do a bunch of consulting and prototyping. Please feel free to contact us. We'd love to do that kind of thing. Okay, in terms of outline, I'm going to talk a little bit about what is the IFO, and then how people have used this agentic Gemini to do this task. And then afterwards, I'll have like a wrap up and also QR code. So you don't need to take photos. I do know that people do go through the link, so that's kind of interesting from other times. So this is what attracted my attention. This is the paper which came out, I guess, a week ago, called Physics Supernova. And this is where they achieved elite gold medals at IFO. So what is the IFO? It's the International Physics Olympiad, which is a competition, like a global competition, like the Mathematics Olympiad, which is more famous, but it's basically from each country, they send five of their top students to compete on this international stage. And well, so Singapore will have a team, the US will have a team, the UK will have a team. And this is all kind of pre-university students. So it's kind of A-level, the syllabus is A-level physics. So it's things like lenses and gravity and all the things you might do. It's not quantum mechanics, for instance. And basically, there's a kind of rotating city where they all meet up and they all do this competition with tricky physics problems. So I'm going to have a quick look. I mean, not many people said they loved physics, which is a bit worrying. I'll have a look at some of these I'll have a look at the 3 theory questions. So each year they have 3 theory questions and 2 experiments. And the experiment questions is obviously difficult to do by AI, even though there's normally one like practical thing where you try and measure something, and there's maybe a computer simulation. So you've got some simulation which you basically probe by firing rays in the computer in some way. Now the second one is probably possible for an agentic system to play with but that's kind of quite a hard task. Okay, so for the 3 theory questions, basically you sit there for 5 hours and you've got these 3 questions to answer. So the first one is about hydrogen and galaxies. So I'm going to go through the things very quickly because I do love this stuff. Another one is about Cox's timepiece. This is a super weird clock in a museum to do with having a tube in a bunch of mercury and it's going to bob up and down to make a clock. And the third one is about champagne. Now this competition was held in France just this last summer. And so they had this is probably the French question, which they stuffed in there. Now, in terms of metrics, these questions have like a fixed rubric scoring scheme, and it actually tells you how you score the points. The paper had an actual previous competitor and someone who'd marked the exams. I have to say that kind of like the Maths Olympiad, if you can't do the question, you write down nothing. Right? It's not like you can do half a question particularly. You either kind of get it or you don't get it. Because it's kind of a tricks-based thing like the Maths Olympiad. Okay, let me just go on to okay, so here's hydrogen and galaxies. So basically the first thing they're getting you to do here is the Bohr model. So this is all about the hydrogen atom thing and how it emits light, and can you get a frequency of light out of a hydrogen atom? So the reason that they're doing that is that they can then say, well, let's look at the spectra of hydrogen orbiting a galaxy. So the next part is all about, okay, what about galaxies? How do they curve? Okay, and then the next part is, how is the mass distributed around a galaxy? And then the last part is, so you can see there's also, I mean, as well as the text and the questions, they've got these diagrams in here. So just to explain what's going on, this is a bit of a hairy diagram, but if you've got a model, it's got to be able to understand that or read the graph, for instance. And then the last piece is to do with MOND, which is a modified gravity thing to explain why galaxies don't spin the way you would expect. So this is an alternative to a kind of dark matter thing. But basically, to understand every part of this, you don't need university physics. It's just cleverly applying A-level physics, basically. Cox's timepiece. So this is like a historical thing, and it's all about some tube bobbing up and down in Mercury. And you basically go through this, I don't know, there's a whole bunch of different things about the oscillations of this and essentially modeling out how this thing works. And then the last one was kind of nice because for the champagne, obviously they have excessive alcohol consumption is harmful unless you're in France. That is, so the first part is all about how bubbles form and how quickly they expand. So basically they give you a bunch of facts, like you can kind of assume this is right. And you can also kind of assume you can answer the question, which is it's actually a pretty significant thing. If they ask the question, you know you can answer it, which is a giveaway in many cases. Okay. And then they also talk about the sound bubbles make when they pop. So this is stuff you can, okay, hopefully you can see that this is like A-level physics, but it's applied in a way which is like very different from what an A-level physics question is, right? And so the last one is about how high corks fly when champagne pops. So this is a very French kind of question. Okay. So the paper is, it's on archive. They used Gemini 2.5 Pro, which I didn't know they used this ahead of time, and they use this kind of an agentic way. And there's a code repo, and the authors are talking on Twitter. Now, one of the interesting things is that the author said, until we can do the experimental section of this paper, it's only going to be good for a workshop. We can't beat the physics Olympiad without doing experiments. Therefore, this is useless. I'm not convinced. I think that it's quite hard. It's technically quite hard to do these theory questions. The experiment, I don't know, from my background, I think the experiments ought to match the theory. So why even bother doing the experiments? Okay. All right, so here is their agentic system diagram. They've got a bunch of, well, really they only use two different tools, one of which is an image analyzer, so they can read the graphs, and another is an answer reviewer, which basically tells them, did you get it? Do you think you got it right? Basically, it challenges the model in a loop, saying, try and answer the question, use tools if you can, but also, did you get it right? I mean, because often Gemini or all these models will kind of claim, oh, I got the right answer. And then you say, you sure? And it's like, oh, no, you got me, right, kind of thing. So here, basically, when they're also saying, oh, you got that was a super great approach. You really thought out of the box there. It's like, okay, anyway, some tactics are required to stop that sycophancy. So basically, they use these two tools. They allowed up to 80 steps to do each part. So 80 loops. This is quite a lot of agency. And they allowed up to 32K tokens output. Okay, so the main image loop, basically the problem solving part is basically your task is to solve the problem part by part, only after you have fished the whole problem. Okay. One thing which is surprising in papers that you'll read is that when you read the actual prompt, they're full of spelling mistakes and grammar mistakes. Like, it's incredible to me. Even the original GPT-2 prompt talks about scientists discovered, not scientists discovered. They say scientists discovered. It's like they got the grammar wrong way back then. It's amazing. Okay, as well as this kind of loop, they also say, heck, here's the image tool prompt. Basically, if you've got to measure something, you've got to use this tool. Don't guess. You're going to get it wrong if you don't use the tool. Basically, they're trying to emphasize the usage. So the image analysis tool is basically a Gemma again. They just say, you're an expert at Physics Olympiad. tell me what's in the image, basically. You know, you've got to answer this question, use the image. So that's a very simple piece of stuff. The one for the reviewer is harder. Basically, you're an uncompromising physics peer reviewer. You have to find every logical mathematical error. But basically, this is trying to make it as critical as possible, because it's quite good at rescuing itself after the fact. But you know, you really have to stop it thinking that what you're telling it is like God-given information. Okay, so as a quantitative and qualitative analysis, basically you've got the first piece here, which is the Bohr model, rotation of galaxy. How is this? Basically, the first bit is super common. Everyone will have done that. But the rotation of galaxy is getting trickier. And then this MOND thing, probably no one's ever seen it before. They're asking weird questions. Same with this timepiece. It's actually pretty novel. And that's kind of one of the things with the Physics Olympiad is it's kind of, they really move you off the syllabus. Sorry, you're on syllabus, but in a weird area quickly. These things aren't terribly difficult to compute. You're not asked to do a lot of calculation. So that's not the problem. But just to just to figure out what's going on in this kind of alternative thing is good. And then here's kind of like, how much do you have to actually understand the images? Do you just have to figure out like what's going on, or do you have to actually measure a peak or something? And so they also look at the top 10% score for the Olympiad, and those people would essentially score a gold medal in the international competition. And so what they found here, they analyzed this across the different stages. They ran it 5 times, and basically they could show that here's what we'd score with only the LLM. Basically, does Gemini get it right? And then if we add this agentic loop, does it score better? And the main answer is yes, it scores better if you do the agent thing, which is kind of unsurprising, but it also means that by running it longer, it can get better, which is like a good sign. So overall, the system scored a certain number of points, which is 14th among the 400 competitors. So this is five from every country. I guess there's however many countries that is, maybe 80. And this is where it scored. This is a good score. Someone asked, was this overfit on this exam? In particular, did they run it tons of time and tune all the prompts? And the answer that the last author gave is basically the budget was just $200. So it was impossible for us to run multiple experiments. And so we couldn't even cherry pick. So they ran the thing 5 times, but they just ran the code in the repo, which is good. They found that the Gemini Pro on its own could score a gold, but like just. Whereas the agentic thing meant it's actually a strong gold, which is awesome. So some observations on this is that the host country kind of affects the style of questions. Now, I mentioned this once in a meetup before, but I represented the UK for the Physics Olympiad twice. So in the UK, the questions were very, very much like what I would expect from a maths point of view. It was like, here's a situation, prove this, generalize. It is very proofy, mathematical. Whereas the German one I did was basically engineering. It's like, here's a design for a thing. Tell us how fast, what voltage needs to be applied to do this. It was very, to my mind, more like in answering a calculation. I did badly on that one. With the UK, I was okay, to some extent. The French one seemed more like lots of hand-holding. There's lots of little steps, but they do lead you down a long path. So there's obviously like a style question amongst countries, which is kind of, but on the other hand, this may have suited Gemini because it broke it up into nice little bits, which it could then do this agentic loop over. The other thing I mentioned is that these simulation experiments might become possible for agents, but it seems unlikely to me they're going to have an Olympiad where they only have computer simulations. I'm sure they're going to want people to get their hands dirty at some point. Okay, so to wrap up, Gemini Pro is pretty good, right? It gets a huge boost from the agentic framework that they had. The exam style may have been a bit helpful. I mean, maybe if they'd have been given the English questions were more like the maths ones in some sense. They made you do a bunch of stuff just swimming out into the distance. They only had a very limited budget to do this, But also, I would say this won't deter anyone from trying to enter this competition. Right? Just because the computer can do it doesn't make me think, oh, why would I bother? It's still like a challenge, and you're still like, this is a genuine thing. So kind of like the Go players, are they dissuaded from playing Go because there's an awesome player? Not so much. Okay, so I mentioned the link to slides. This is a link to my slides. So, hopefully you'll see what was happening in the Physics Olympiad, and you loved that stuff. I also want to mention that after our next speaker, typically what happens is we'll come to the front. The people, obviously people may leave if they want to. We can have a chat at the front, and then when Rakuten throws us out, we suggest that La Passat would be a good place to go. It may not be the very best place, but it's also definitely not the worst place. And there's tons of seating and lots of food choices. And so for the hardcore, our after party, La Passat. And with that, I will take questions. So, and also move on to the next speaker, who should be prepared. Any questions? Any questions? Yes.
Why do you think they didn't use the image capability of the model and instead chose to use a tool for the image understanding?
I don't recall why they said this specifically, but I think that the idea of having a manager and individual tools, even though all of these things were Gemini, the fact that they were given specific roles kind of narrows their scope. So it's not that the manager one is saying, oh, I'm trying to answer the question and I'm trying to think all these different things. It's like, if you want to use a tool, use this tool. Just by restricting their scope actually makes it into, also the system becomes more controllable, and you can more safe in a way, because you can actually say, well, what is being asked of this thing? So this is kind of another undercurrent with these agent systems, is that from a safety perspective, you may be you're in better hands than just trying to figure out what this thing is thinking for itself. If you can see the messages being passed, you can have some semblance of like control. Or is it trying to, is there a module which says, how do I lie? That would be is there a deception module? If it had to call the deception module in order to deceive you, that would be great to know, right? You also don't want it to be calling that module, but if you see what I mean, by restricting the scope, that's kind of a valuable thing. Anyone?
Did they mention like what sort of guardrails or evals or like what they?
It seemed that this was kind of a YOLO paper, in that they basically they got a framework, said let's just throw these Olympiad questions at it. Did it work? It worked surprisingly well. Okay. They also know that the people have actually looked at Gemini Pro for the maths Olympiad, and the standard model there isn't particularly good at delving into the full length of the questions. Though internally to Google, it's a very Gemini-like model, I believe, which did the maths. Obviously, they turned up the parallelism enormously, and also, so they're trying to do it 1,000 different ways, and also let it think for as long as possible. 1.5 hours is quite a long time for a Gemini to respond. So this is just the regular public model, which is quite impressive. Okay. Oh, one more. Last one.
Any idea why big AI labs focus so much on the math Olympiads, but not so much on the physics?
Well, I think the maths, in a way, the maths is appealing to mathematicians and maybe computer scientists, because they're also interested in the informatics Olympiad. The physics one has the experiments, which they know is going to be very hard to get to. So maybe that's an issue. I guess another thing is that the math stuff, that they can ask questions, the math syllabus. So the maths one is slightly unfair, because a lot of the questions have a lot of combinatorics or like number theory, which really isn't a school subject. I mean, if you're super into maths, you know all these tricks about how to deal with prime numbers, but at school, you don't necessarily learn that as part of your A-level. So you may learn like Fermat's little theorem or something, but basically people who are good at the Maths Olympiad, they really have all the tricks up their sleeves. For me, it was kind of an amateur hour. The UK kind of assumed that if we just turned up for a weekend to have fun at the competition, that was good, right? Whereas we know that the Romanians had a whole college to do this. It was, people take it very different levels of seriousness. So it's kind of an interesting thing. We had one guy who kept, sorry, I digress. We had one guy who was on the team who just came from the Maths Olympiad. And he's like, oh, it's great to be amongst like normal people. So we weren't strictly normal people, but he said that the Maths Olympiad, they were really out there. It's like, so it's kind of interesting. And yeah, so I myself, I tried the Maths Olympiad questions. I'm pathetic at the Maths Olympiad. Maybe I could try a bit more now. But back then I was useless. The physics felt natural to me. So it's definitely a kind of how your brain is wired kind of thing. Anyway, let me hand over.
Hello. Okay. Okay, let me share my screen. Oops. Which one? Presenter. Should be. I don't know which one to share. What was this one? Pretty hard. I think so. This one? Oh, cool. Okay, so welcome guys. I'm pretty excited to meet you guys at this wonderful night. And the topic I'm going to talk about tonight is efficient inference and serving of large language models. And we will go through a little bit about video generation models as well. And so before beginning, I want to ask you guys several questions, like how many of you guys have be familiar with the concepts of inference and serving of large language models? Okay, cool. And how many of you guys have worked with machine learning system guys? Okay, cool. Then I think this presentation for people who are familiar with inference and serving and who have familiar with the concepts of MLCs is it will be a good retrospection of what researchers and the industry developed in the previous years. And for people who are not familiar with these concepts, it will be an introductory journey to guide you into the serving and deployment of how to use those models to support real-world applications. Okay, so this is today's outline. I will start from the introduction to large language models, from the components and how we compute the key points of it, to inference and serving. And then we will go to the challenges we have at this time, and then we will look at some example methods and ideas of how we improve the metrics as well as resolve the hardware challenges. And then we'll go to the video generation models. So about myself, my name is Jonathon, and currently a senior software engineer at Rakuten, focusing on enhancing AI products. Okay. So, okay, let's go to large language models. I think in Martin's presentation, he has mentioned the agentic workflow, which applies different agents, including applying the Gemini Pro. And so nowadays, I think there are many products which applying the capability of large language models, like the chatbot, the AI assistant, and like the AI augmented search, like the knowledge base, like the productivity tools, like Cursor. Like how many of you use Cursor or Cloud Code or Copilot daily? Yeah, the same for me. I like Cloud Code the most. Okay, so behind these AI products and applications, this is the application of utilizing the large language models. So I put a figure of the most fundamental paper here. That's the attention is all you need from Google Research. And they provide a mechanism of attention as well as the transformer blocks, which become the fundamental components in later study and applications. So we will start from the self-attention and to the transformer blocks, and then to the model themselves. So let's move to a simplified flow. Okay, so this is a pretty simple flow, ignoring some calculation details, but let's just focus on the two words, welcome to. And you can imagine the welcome and to, the two words get tokenized and go through an embedding layer and become some hidden states. And then these hidden states are just like representations in higher latent space, which contain the information of those tokens or of those words or parts of words. And then these hidden states will be multiplied with the parameters of the model, become QKV projections, which we will talk more later. And the QKV projections will be multiplied together, and first Q and K, and then K and V. And then we got the output context. Okay. And that's basically the flow of self-attention. And we have more and more variants of self-attention mechanisms in the subsequent years after 2017. But we'll just use the basic one to demonstrate the ideas. So the idea of attention is like you have a sentence, you have many words of your sentence or many sentences in your paragraph, and you want to generate something. You want to ask further questions. So you want the generation knows the context of your input, right? The context should like different parts in your paragraph, like different words in your questions. You want the answer accurately reflect those contexts. So that's why we call it attention. Is it can make each component of your input to attend to each other, saying that the third words can know the existence of the first and the second words, and know the existence of the following sentences. So that's the goal of attention, self-attention. And the self-attention, as well as like a feed-forward network, will form a transformer block. And we have multiple transformer blocks stacked together, which become the main body of a large language model. So this is a simplified generation flow. It's like you have your input prompt, and it go through a tokenizer and become a tokens here. But I just put welcome to here, but it actually not these two words if you're in real scenarios. Yeah, and then it will go through the embedding layers, which become hidden states, which become like representations in higher latent space, and those representations will go through the stacked transformer blocks, and then go to the output head or the prediction layer, and we got the outputs on the vocabulary set. So that's a basic flow to generate a token for a large language model. And then we move to inference and serving. So what it mean? So once you have a trained model, whether it's a pre-trained model or a fine-tuned model, you want to use it, of course. Then if I don't use it, why we train that, right? So how do we use these amazing models? We want to deploy the models, and this process we call it inference. It's like I input some prompts into it, and it will generate outputs to you, like one token by one token. So if you use Cursor or ChatGPT, you can see your output is generating like in a streaming way, right? It's not generating a whole paragraph or a large block or a chunk. It's generating in a streaming way, like a word by word or parts of the words by parts of the words. So that's we call it autoregressive way. It's like for this tool, it will use the context, it will use the caches from the words before. And then once it's generated, the KV of it in the self-attention component will be stored as KV caches. And then it will generate the next token, which is day, and then one by one. So that's why when we use ChatGPT, it's generating in a streaming way instead of a diffusion way, instead of a chunk by chunk. Yeah. And for the image and video generation models, we'll just raise diffusion transformer at here. So it's iteratively denoising in a diffusion way. It's like it encode the noises, the image into a latent space, and then do iteratively sampling from the noise. And that's a way, kind of like a diffusion way. But for LLM, we mainly focus on the autoregressive way. Yeah. Okay. Then for serving, serving is like since inference is just like you input something and it generates tokens one by one, right? It's kind of like a lab stuff. It's kind of like you want to try a single run, but it's not a way that to serve a real world applications. Serving is like to consider the complex scenarios of the real world application, as well as the limited resources you have, and to see how we can optimize the system and provide higher throughput and lower latency, and to serve like multiple different applications. So this is a naive serving diagram, which we might have like different optimized models, and we might have a scheduler to dispatch your requests and schedule the inference. And we have the hardware considerations. We have a cluster. You might have clusters of resources in different places. So these are all the considerations we have, like when we serve for real world applications. So let's move to the LLM inference stages. So we have mentioned that LLM is an autoregressive way which generates token one by one. And so there are two stages we should note here. The first one is prefill stage. You can just consider prefill stage as the time to process the entire input prompt. It's like you input welcome to today, you input these words, and it first process in prefill stage, which can do the computation in parallel way and store the KV caches in your system, actually in your high bandwidth memory of the GPU. And then you move to, once you have the context, once you have the caches of the context, you move to the decoding stage, which generates new tokens one by one. It's like when you have the welcome to today, and it generates a catastrophe S, and then you have the caches for S, you put it into your memory, and then you generate for the next one, sharing. Welcome to today's sharing. Yeah. So this is there is a actual stage called append stage, which might come across in some inference systems, but we are not going to cover it today. Yeah. Okay. So we have known there are two stages for the inference, and we have known some real world scenarios of how we use the AI assistant, how we use the large language models. Then there should be some concerns, like nowadays the models have more and more parameters. It become larger and larger. So several years ago, you might use a llama 7 billion parameters model, and that seems to be enough. And then it become 70 billion, and then it become 600 or 700 billion. And nowadays it even we have there are some open source models which has over 1,000 billion parameters. So the models become larger and larger, which cannot be held in a single device. And then the context in a real world application, you might have a chat, like multi-turn chat, right? You might ask questions, ask the second questions, and a lot of questions, and you might input some documents, which makes it a pretty long context to process. So the context gets longer and longer, and some of you might find out that we mentioned KV caches before, and if you have a context gets longer and longer, the caches gets longer and longer, and seeing that at least it gets a linearly increasing, and you cannot hold infinite context, of course, since you are linearly increasing your KV caches at least. Yeah. And then you should consider like the large number of requests coming in, like how we should batch them together and process them in limited resources. So before considering the metrics such as latency or throughput, let's see how we can make those large language models runnable. Oh, this is a nice picture I pretty like. It's from NVIDIA. Yeah. So these are some example devices which people use for training as well as inference. And we had most of the time you might use NVIDIA GPUs. So it has different series like MP, Hopper, or the latest Blackwell GPUs. So for these GPUs, they have different size of HBM. So I'll introduce HBM later. And we also have there also have other brands like AMD, like some of the RDUs, which these are all designed for the AI works, such as training and inference. Okay, so when we talk about the device memory, so I've just pasted a screenshot about my activity monitor at some time, and you can see there the occupancy of the physical memory and the cache files and the swap used. So currently it's nice since not too many memory consumed, but if I open more apps or open more documents or more tabs of the Chrome, the memory consumption will increase drastically, and then you can see the swap use might be increased as well. But the memory for your MacBook and the memory for the devices you use for AI works are pretty different. So the memory here, in common cases, we talk about the HBM here, which are near the chip of GPUs. So these are called high bandwidth memory, which has a relatively high bandwidth. You can see here, the green part, HBM. It has a relatively high bandwidth and have a relatively large space. It had 40 gigabytes. That's for one of the series of MP 100 NVIDIA GPU. So for SRAM, so why we cannot increase the size of SRAM? That's because SRAM is a memory on chip. Is just you can see here. It's on chip, which means it's not packaging together, but inside it. Yes. So commonly, we will put the models into the HBM, and then the models will be loaded and the parameters will be loaded to the SRAM during the computation. And during inference, like what occupies the device memory? Of course, we think about the weights, the parameters of the models. If you have a 7 billion parameters model, then the weight consumption will be about 14 gigabytes, saying that you use half precision, like floating point 16 or B float 16. And that's the part of consuming the most of the memory. And then the second is the KV caches we mentioned before. KV caches will increase as your context gets longer and longer. When you generate a new token and its KV cache is attached into your memory. And then the third one is activations. So activations here sometimes might be confusing because you can consider that as intermediate results, like intermediate tensors you should store in your memory and use later in subsequent layers or subsequent computations. Yeah, and you might have some extra buffer context usage, but that's commonly cost less memory. Yeah. Okay. So memory is always expensive, and people come across many ideas to overcome the limited memory. So one of the trick work here is the sliding window attention. So what it does is not going to use the exact full attention mechanism. It will use it will control a sliding window to move your to focus on only part of your context. Like the thing that the window size is 4,000 tokens, then as your context become longer and longer, and it may generate tokens like more than 4,000, and this mechanism will only focus on the latest 4,000 tokens and generate new tokens, which means it actually forgets what your oldest parts in your paragraph, in your input. It just focus on the latest parts of your input and the latest parts of the generation contents. But with this way, it can support like nearly infinite context length, but here the support might not be accurate since we just forget a lot of things. Yeah. And then we have the flash attention. This is a pretty famous work, which also enlightened some good work in subsequent years. So the idea of flash attention is to reorder the computation to avoid the forming the full attention memory consumption. Instead of computing the attention score at once in our previous simplified flow, it processed the queries and keys in tiles, which is like in blocks here, like in blocks and one by one, and finally collect the results together. And you can see the SRAM here, what it do is it just loads parts of the Q, K, and V into the SRAM and do computations with the data in the SRAM, and then move to the second block, the third block. So in this way, what it saves is the time costing of moving data from the chip to the high bandwidth memory. It's just focused on the SRAM usage, and instead of to calculate the whole results and move the whole results between the chip and the memory. And so that is also decrease the latency a lot. So the previous two examples are methods like enable you to calculate, enable you to feed models and get longer context in a single device. But what if we cannot even fit the model parameters in the single device? Saying that we have a 70 billion parameters model, like Llama 70 billion, we cannot fit it in A100, which has only 80 gigabytes memory, and we cannot fit it in the Hopper GPUs as well, right? So we have to make some parallelism. There's an example of MLP tensor parallelism, which you can, it doesn't matter if you don't know the concepts of MLP, you can consider that there are some matrix multiplications, which we have the X as input and Y as output, and the A and C are model parameters, and B is the intermediate results. So once we input the X here, we input the X, and it multiply with the model parameter A, and we got the intermediate result B, and B multiplied with C, and we got the final result Y. So this all happens in one device. And imagine if we can split some of the tensors, or just consider matrix, some of the matrix, to split them into two devices. And so for parameters A and C, we split them into two devices, which noted here. And you input the X in both of the devices, and to multiply with X A1, X A2, and you got B1 and B2. And then the two intermediate results, this one is on device, the first device, the second device, and then you multiply them with the corresponding splitted parameters, C1 and C2, and you got Y1 and Y2. That's the results in each of your devices. So you can see the shapes of the output on each device is the same as the previous one, is the same as the original one. So why it happened is you can see the dimensions of the matrix, and it's pretty clear it's pretty clear for you to get the same shape of results here. And then the two results have to be collected together, to be merged together to get the exact original results of Y. Since you are doing partial computations, and you have to utilize some communications between the devices to collect the results. So here we use all reduce to get the final results. So that's a basic example about how tensor parallelism work. The idea is to split the model parameters and utilize some communications between devices, and then get the results. But you can see we input the same, we have the same input. The input is not splitted. So it can also be considered as a type of data parallel. Okay, then let's move to the other example about parallelism. It's about sequence parallelism, which is also a pretty popular idea in previous years. So the sequence parallel, the sequence represents your input. We just call the sentence as sequences. And for here, you can see this is sequence parallel. And the sentence or the sequences is split into two parts. And one is feed into the first device, and the second part feed into the second device. So we mentioned we have the context get longer and longer, and you have the KV caches get larger and larger. So in this way, you can see you split the KV caches into two devices as well. And there is also modifications on the attention mechanism. But here, we are not going to deep dive to the algorithm, but you can see if we have 4 devices here, and when we calculate the KV projections, we calculate it in a block-wise as well. As one device calculate one part, and then send the results to the second device in the ring way. So basically, the ring attention idea is to split your QKV projections across the N devices and exchange the segments. And the one pass completes when every node has seen all parts of the KV. So that it can approach relatively like four times of context, 4 times of length of the context it originally supports. Although it might cause some actual communication latency in inference loops, and the higher costly cache management, but at the system level, researchers and the industry can make some overlapping to hide the actual latencies. And then let's move to like other methods and ideas of serving real world applications. The metrics we might pay attention is the latency, like the time to see your first token, and the throughput, the tokens per second, as well as the end-to-end latencies. And we want to improve them as well. Actually, we have mentioned some of the methods to improve the latency. The parallelism, you split the computations into different devices, you have more resources, and then it's, of course, in common cases, you improve your latency with parallelism. And then in algorithm side, there is speculative decoding, which is applied in industry at this time. The basic idea is you have a drafter model, which has fewer parameters, and you have a target model, which has a larger model, has more parameters. In common cases, it's like 10 times parameters or what. Yeah. And when you input a sequence, so here we have welcome. You input the context, and then let's ask the drafter model to iteratively generate tokens for 5 times, right? Welcome to today's lunch. It will iterate for 5 times. In each iteration, it will generate a single new token, and then we'll pass the results as well as the input context to the target model, and let the target model determine if the drafter model performs good or not. So here you can find this drafter model generates tokens in 5 iterations. But when you pass it to the target model, it can consider this as an entire input prompt, which is the entire context. So that it's just not, instead of going to the decoding stage, is processing in the prefill stage, right? It can process the whole input in a parallel way, which is the prefill stage we mentioned before. And then it will say, okay, the processing I've done, and I found that the launch, your launch is not consistent with my results, and so that I'll ask you to regenerate from the token before the wrong token, and then this result will be passed back to the drafter model, and the drafter model will start from S to generate the future tokens. So why it's important? Since the drafter model is much more quicker than the target model, so that if the drafter model can generate like more correct tokens, and we will have a pretty we will get a lower latency here. And the drafter model still needs to be trained to align with the target model, so that it will increase the chance it get the correct or aligned outputs. And then there is some exist some overlappings at different levels. We have the sequence level, like the batch level. You might have multiple batches to be processed in your system, so that to hide the latency of communication between devices. And for system level, you might have some checks on the sampling as well as the scheduling, of the request, and the sending and the launching of the kernels. So the idea is to hide the latency between the communication and the computation, as well as the latency between the two stages, as well as the latency between different requests. And there's a prefix caching mechanism. I think many of you has seen the OpenAI API pricing here. Like, have you used OpenAI API in your AI products? How many of you have used it? Okay, cool. So the pricing here, you can see the cached inputs is pretty cheaper than the original inputs. So why it happened? Because the calculation, the computation to get the KV caches are computational intensity tasks, and once it computes the results of the caches, it will store the caches for some time. So you can see OpenAI provides a statement of the cache are typically cleared after 5 to 10 minutes. So which means that if you don't have more subsequent chats in your threads, it cannot be fit into the previous contact. If it cannot be fit, then it will clear the KV caches which stored in their system. But when the cache hits, when the cache gets consistent with your inputs, then that will save a lot of time to get your output tokens, to get your output results. And then we move to the auto scaling or elastic scaling. I think this is an issue. This is an issue that which company should consider. The company with its own hardware, with its own services, should consider the most, because you might have like saying that 10 or 20 or 30 or even more nodes of NVIDIA GPU, and you want to train some models as well as to serve some applications in its spare time. You don't want your GPU to just leave it here. Even in night, you want it to run. You want it run all the time, so that the cost will be low. Otherwise, it will cost a lot when it has spare time. So there are 3 categories of tasks here. The first is training. Consider if your company want to train or post-train models by yourself using your own resources, and that's a task you can assign specific time to do, saying that at night or during the weekend. And then you might have deployment which serve different applications, and then you might have a cloud service that's like a renting of devices to other people or to other companies. So these different categories of tasks should be scheduled in a nice way so that to decrease the GPU spare time. You wanna all the GPUs run all the time. Yeah. And about large video generative models, we'll just provide a quick overview. So this is an example video generation platform. It's from Flux AI tool. That's a pretty typical AI video generator, which you can modify parameters like the sampling steps and the guidance scale, and you can also generate videos from the image. And that's basically based on the diffusion transformer architecture, which is also one of the fundamental research work in the video generation scope. And the idea is to replace replace a specific part with attention mechanism. So it's kind of like a UNet backbone or a transformer that denoise a 2D latent that's for text to image, and for text to video that's it's mainly use 3D convolutional layer, and it has attention over time plus attention over space. So for the diffusion transform models speed up, we might first consider the distillation on sampling steps, which can drastically tremendously decrease the sampling steps of a model generation. We mentioned that's iteratively denoising steps, which is like to make your results, make your output more clear and clean by step. And when you have when you fine tune the model based on the original model, it's not fine tune actually. That's a distillation, but on the sampling steps aspect, and you might decrease the sampling steps to 1 to 4 steps, like what Flux Chanel was doing. And so in this way, you get a thing that in previous example, it might take your 10 seconds to generate the image, but with the distillation on sampling steps, you just got like 1 second to generate your image. And there are also some other techniques to decrease the latency, such as there's trade-offs between the time and space. Like since it's a iteratively denoising step, there might be some similar patterns between the subsequent steps, and we can store the intermediate results in some in the memory, and at the subsequent step, you don't recompute this part. You just reuse this part, which has similar patterns between two consequent steps, and so that will save a lot of time of recomputing, but it will consume like more memory on your devices. And then let's go our wrap up. Sorry for taking more time. And so we go through from the concepts of attention and transformer blocks. We go through like how we compute a basic component of large language models, and we go to the inference and serving part, like go through some examples and methods of how we overcome the hardware challenges. During this process, we have some techniques such as speculative decoding to improve the metrics. And then we have the system level considerations, like how you should utilize your GPU and how you should consider the serving and consider the applications you have. Okay. And these are the citations for the previous slides. Thank you. Any questions?
Rather than us taking questions right now, let's have the speakers at the front, after a quick wrap up, so that we can answer questions then, right? You chair. All right, I promised a quick wrap up. Thank you all for coming to this month's Machine Learning Singapore meetup. Our next one is scheduled to be on the 15th of October at Google. We don't yet know the overall topic. I guess today was more like production. We'll see. We typically aim for talks for people who are starting out. Maybe that was embeddings today, or maybe the physics one. Something from the bleeding edge. This will probably be more like the production at serving, and also some lightning talks. I'm not sure what to say about meetup.com. We've obviously experimented with Luma this time, so I guess I should ask a couple of questions. How did you hear about this event? Was it from the meetup email? Ooh. Was it from something from Luma that you heard about it? Some, okay. Did you find out about it through some kind of messaging group? I know that some people like talk to, okay, what about just like people you talk to who tell you, oh, there's a thing happening, we should go, kind of thing? Anyone? Okay, interesting, okay, slightly different. All right, and how do you feel about Luma versus Meetup? Who thinks that Luma's better? Oh, and how many people think that Meetup is better? Okay, how many really don't care as long as the... Okay, that's good to know. All right, so now we know, right? okay, know something at least. So obviously, if it's on Meetup, make sure you check where it is and where you're meant to be signing up. This is the list of people who are on Meetup who joined the waitlist, despite the full instructions. Don't join the waitlist. Okay, so this is I'm ridiculing these people. They may be in the room, or they may be standing around at Google wondering when we're going to turn up. So I don't know. Anyway, there's a huge number of people at Google, which also makes it difficult. So on Meetup, which also makes it difficult to plan how many seats do we actually need. There's more. Oh no. Oh no. Okay. All right. So with that complaint behind us, thank you very much indeed for coming. As I said, we'll have a quick gaggle here until they throw us out, which was meant to be at 9 o'clock. And then the hardcore will go to Laposat, and we'll chill out there. Okay, thank you very much. Oh, and thank you to our volunteers.